Wonderful. Welcome. Good afternoon, everyone. My name is Lu Li. I'm the interim chair of Department of Physics here. I'm delighted to welcome all of you to the 33rd annual Tayo Wu Lecture in Physics, presented by Professor Gabriela Gonzalez from Louisiana State University. UM Physics Tayo Wu Lecture honors one of our most distinguished alumni, Dr. Tayo Wu, and this lecture series was endowed by his friends and admirers. Dr. Wu earned his PhD in atomic and nuclear physics from our department in 1933, and then started a career on scholarship, teaching, and leadership throughout many different places. He's known as a father of Chinese physics, not only for his leadership in the other side of the earth, but also from his leadership across many countries, as well as bringing Chinese physicists to these countries. His former students, T.D. Lee, as well as Sen Yang, shared the Nobel Prize in 1957, my bad. And were among the first physicists to deliver Tayo Wu lecture. You can read more about Dr. Wu's life and legacy in your program. Again, as the very first Asian origin, I think, chair in this department, interim chair at this department, I want to share a few experience about Dr. Tayo Wu. I remember as a major student in physics, back in my college in China, there's two things I have to work through. One is his book, the famous series of books, of course in Chinese first and later translated to English. We have to study both to know the terms. And then the program series or program sets for Caspia. Caspia was led by T.D. Lee, one of the students who gave the lecture earlier, I think it started in 1978, and for about 10 years, that brought many colleagues, many physicists to study in USA, including a few of them in our faculty here. Me, as many as others, were able to come here only because of Dr. Tayo Wu. We're here thanks to his starting leadership. We're here to study, do research, teach, and work with every one of you. And now, without further ado, let's have my colleague Keith come here to the podium, and please welcome Professor Raff.
Okay, thank you. Everyone can hear me? Yeah, okay, great. So good afternoon, everyone. It's a real pleasure, a special treat, a personal treat for me to introduce this year's Tayo Wu speaker, very distinguished physicist, Gabriela Gonzalez, who is the Boyd Professor of Physics and Astronomy at Louisiana State University. My mic is on, I just don't talk loudly enough. That's the problem. I'll move it closer, see if that helps. Okay, so I first met Gabi 28 years ago when a bunch of us came together at LSU to form the LIGO Scientific Collaboration known as the LSC. We were a very diverse group of scientists from many different fields. As a high-energy physicist, that is to say a newbie to this intriguing new field of gravitational wave science, I looked to established experts like Gabi to help me to understand the instrumentation of gravitational wave interferometry and to understand some of the pitfalls of analyzing the data that those interferometers produce. And over the years since then, I have indeed learned an enormous amount from Gabi. Some of it technical and some of it sociological. On the technical side, I've learned in some sense how exactly you do calibrate a free-swinging suspended pendulum interferometer and how to measure the Gaussianity, or actually more to the point, the non-Gaussianity of the data produced by such a free-swinging interferometer. But on the sociological side, what I've learned from Gabi from watching her over many years is how to herd physicist cats. So as many of you know, Gabi was the LSC spokesperson, that is to say our elected leader, thrice elected leader, at the time of the discovery of gravitational waves in September 2015, just over 10 years ago. She had led us for more than 4 years at that point through this period where we transitioned from initial LIGO, which was the era of possible detection, to the era of advanced LIGO, which was meant to be plausible detection. Now, what very few of us appreciated at that time was that plausible actually meant likely. Fortunately, Gabi was one of the few who knew to prepare for likelihood. And so, thanks large part to her leadership of the LSC, we were ready and able to make that discovery in 2015 and to capitalize on it with a slew of papers that opened up a whole new field of physics. As you may also know, Gabi was elected last year to be in the presidential line of the American Physical Society. She is currently the vice president. Next year will be the president-elect. And in 2027, the president. In 2028, the past president, if I got that sequence right. Okay, good. So in other words, for her success in leading the LSC, she has received a sentence, a 4-year sentence, to do the same sorts of things for the American Physical Society. And I think that the qualities that served her so well as LSC spokesperson will serve us all well in these very challenging times. Gabi has won too many prizes and awards for me to list them all, but let me mention some of them. She's an APS fellow and has received the APS Edward Boucher Award. She is also a fellow of the Institute of Physics, the American Astronomical Society, and the International Society of General Relativity and Gravitation. Some of the recognitions she has received include the National Academy of Sciences Award for Scientific Discovery, the Bruno Rossi Prize, the Albert Einstein Society's Einstein Medal, the Gruber Cosmology Prize, the Breakthrough Prize in Fundamental Physics, and many others I am omitting for brevity. Last but not least, Gabi is an elected member of the National Academy of Sciences and of the American Academy of Arts and Sciences. Please join me in welcoming Gabi Gonzalez to the University of Michigan.
Great. But of course I did, and I will tell you that everything I did, everything we did it because we had a great team that took 30 years in getting here together. And I'll tell you more about that. That's one of the other matters I wanted to mention. So I've tried to make this talk general enough because the details, if I dive into the details, it can get very complicated. But please do ask me. And if you want, you can ask me questions while we talk. There are microphones there. If not, I'll try to leave time for questions afterwards. But I can warn you, I often run out of time. But I love questions. First, Einstein theory. I don't know how many of you have taken a general relativity theory course. It's one of the most difficult courses I have taken. And it's a lot of math, but the concept is beautiful and very, very simple. The concept is that it's a theory of gravity that instead of thinking about forces between masses, which is what we learned from Newton's theory, is about masses living in a space-time, which I represent like a two-dimensional grid, but it's a three-dimensional grid with clocks. That's the time part. It's a space-time. And what masses do, instead of attracting each other, is they modify, they change, they curve the space-time. So the clocks, if there are no masses, all the clocks are synchronized and all the distances between the corners are the same. But if there are masses, then the clocks are not synchronized anymore. They run at different rates near the masses and farther from the masses. And then when there is another mass, like the Earth in here, it will see the curvature and it will follow that curvature. So the Earth goes around the sun, according to Einstein, not because there is this force, but because it's following the curvature of space-time. No math there. It's beautiful. It's a beautiful concept. But again, the math is very complicated, and it produces predictions that were verified very soon after, like the deflection of the light when it goes near the sun, like the precession of the perihelion of Mercury. So there are lots of predictions that tested the theory of gravity, and it was right. Now, the other prediction is that if you have two masses, and these are two black holes that I like to say are dancing the tango because I'm from Argentina. And if there are two black holes, there are going to be curving space-time. They are going to be orbiting around each other. I mean, Newton already predicted that. But then the curvature is also going to be orbiting. So that curvature, it's going to be moving away from the masses. Those are the gravitational waves. They're going to be carrying energy away from the system because gravitational waves carry energy, which means that the two black holes are going to get closer and closer together until they merge. So that's a prediction. According to Newton, these two masses would orbit around each other forever. According to Einstein, they would produce gravitational waves and they would merge into an object. Very, very different prediction. The problem is that when you put the numbers in there, and people actually put computers in here, this is a numerical simulation of two black holes, then they can predict only with computers, not just with pencil and paper, what's the curvature near the masses, which is going to be a very, very large curvature, and also what is the gravitational waves that are going to be traveling through the universe far from the system. And near the system, everything is very complicated, and this is a movie that it's going to slow down in time as the black holes get closer and closer, orbiting faster. These are black holes that are going to be orbiting at half the speed of light before they merge. Here the movie slows down, but this is when the black holes are moving the fastest, and then they merge into a single black hole, and then there's a little ring down, and then at the end you have just a simple black hole that is rotating. That rotating black hole, according to Einstein's theory, does not produce gravitational waves. Because the theory says that to produce gravitational waves, you need to have what's called a mass quadrupole, which means non-spherical. Anything that's non-spherical and it is moving, it has to be accelerated, will produce gravitational waves. I like to say that when I talk, I move a lot, so I am producing gravitational waves. My husband, who knows quantum gravity, says, you're not producing enough energy for a single graviton. So, but classically, I am producing, according to Einstein, I am producing gravitational waves. The gravitational waves would look like that, far from the source. They are waves of space-time, which sounds mysterious, but it just means that distances, space, it's going to get longer and shorter, longer and shorter. That's a wave nature. But as the masses go closer and closer, let me put the movie again, then I want that thing to go away. This is a wave. As the black holes get closer, the frequency is going to increase because they are moving at a faster orbital frequency. Because they're moving faster, the amplitude is going to increase too until they merge. And after they merge, there's going to be a ring down of that last black hole, and then nothing else. Nothing else, because in the end, what you have is this perfectly spherical black hole that is rotating, but it's spherical. It doesn't have a quadrupole. So this system produces a gravitational wave that ends here. Now, of course, if this was not a black hole at the end, if we had a star with a little mountain, then that star would have a mass quadrupole, and then that star would be producing gravitational waves. If it is a black hole, then it's perfectly spherical and it's not producing gravitational waves. So this is not the only the only system that produces gravitational waves, and I'm going to tell you more. But the one thing that the theory says too is that when you put the constants in there, it's a theory of gravity, so you have Newton's constant of gravitation. It's a relativistic theory of gravity, so you have the speed of light. And when you put those things in there, the prediction is that even if you have black holes, big, many tens of solar mass black holes, and they are not that far away, or if you have, for example, 2 neutron stars in the Virgo cluster, things like that that are plausible, this change in distance is not measured in meters. It's a change in distance, but the amplitude of the gravitational wave is a fractional change of the distance. So we are going to divide the change in distance by the distance. If we are measuring a longer distance, then the change in distance is going to be larger. The strain amplitude is predicted to be of the order of, and this is going to be a small number. And when I say small, many people think, well, a part in a billion, a part in a trillion. A part in a trillion is 10 to the minus 9, 10 to the minus 12. This is going to be 10 to the minus 21. It doesn't even have a name that I know of. 10 to the minus 21. That's like comparing an atomic diameter with the distance between the Earth and the Sun. So Einstein himself, when he published a paper on gravitational waves, he published general relativity in 1915, and then a paper predicting gravitational waves in 1916, with some mistakes, because he made mistakes. He calculated, put these constants in there, and they said that's a negligible effect. And that was it. In fact, there was a lot of controversy over decades on whether gravitational waves carried energy, whether they were physical or just a mathematical artifact. So that's a prediction. And like I said, there are several sources. This is the easier one to calculate, at least when they are far away and we can make approximations. But if we have a single a star, a rotating star that it's not perfectly spherical, then it will produce gravitational waves. And those will be sinusoidal gravitational waves. They will not end like at the merger of the binary systems. These we call continuous waves, and these are the ones that Keith is an expert on. We also look for bursts of energy, and that is what you would expect to see or to hear, like we like to say, from a supernova explosion. A supernova explosion is not completely symmetric. It's a burst, so it would produce gravitational waves. And also a background, a stochastic background. That's just like noise, a humming noise that exists at all frequencies with different amplitudes. In the beginning, we said, oh, that's the early universe. And it's true. The early universe produces gravitational waves. But there's also another noise that we are most likely, and maybe it has been detected already, that's the astrophysical background, which is many of these binary systems that are too far away, so they produce signals that are too weak to see them individually, but all together mix up and produce this noise, a stochastic noise. It's a name we give it to them. So these are all kind of things that we look for. And I will tell you about detections that we have made with LIGO and Virgo detectors of these systems, but searches about all of these. So LIGO. LIGO is the Laser Interferometer Gravitational Wave Observatory, and you should all know about it, not only because you like physics, that's why you're here, but also because you all paid for it. This was funded by the National Science Foundation, and this was a project that started, it was being talked about in the 70s. Ray Wise was the first one to think about building interferometers to detect gravitational wave. He proposed that in the 70s. He convinced Kip Thorne theorists, the black hole theorists, that this was a good idea. The two together began talking to the National Science Foundation, and they proposed it. It went through ups and downs, and then in the late 80s and early 90s, LIGO was a project that was funded to build two facilities. The idea, and I didn't put movie here because I wanted to make this a bit shorter, but the idea is to have a Michelson interferometer that you might have heard about. It's a system in which we have a laser at the corner, and then the laser is split in two by a beam splitter. So there's one beam going that way and another beam going this way, and there are mirrors at the end. These LIGO detectors are 4 kilometers long. Light gets reflected here, so now you have two beams coming back. This beam is going to split in two again, so there's going to be half the beam going there. This beam is going to split in two again, so there's going to be two beams coming out here, one from this arm and one from that arm. If these two distances are the same, then we don't have any light at the output. But if these two distances are different, then the two beams are going to be not completely out of phase. There's going to be some phase difference. So we are measuring the interference of two beams, and that's why we call this an interferometer. And the phase difference of the two beams that come out here tell us about the difference in these two distances. Now, this is another property of Einstein's theory, that these waves are quadrupolar waves. And that's a fancy way of saying that if the beam is traveling towards you, then when these distances get longer, these get shorter. And when these get longer, these get shorter in the perpendicular direction to the travel, to the direction of travel. So the idea is that if there is a gravitational wave coming through Earth or below Earth, because these gravitational waves can go through anything, then when this one gets shorter, this one gets longer, which means that at the output, we don't have completely destructive interference. We have some light. So if we put a photodetector there and we measure more light, less light, more light, less light, that's a gravitational wave. Or maybe this mirror moved. Or maybe the laser glitched. So we need to take care of all of those sources of noise to distinguish them from gravitational waves. Now you can see that these are 4 kilometers long, which makes them very expensive. And not only that, but we have two detectors in the US. There's one in Hanford, Washington, and one in Livingston, Louisiana, very close to LSU. So I am there as often as I can, which is not as often as I like. But there are two, and they are very, very far away. And why would you spend twice the money? Why would you build two of these? Well, that's because this signal is so small, and it had never been seen before. And it was something that you need to distinguish from the noise that I will tell you about. Then you need to have some way of confirming it's from astrophysical origin and not from something moving the mirrors on the ground. And the best way to do that is to have a coincidence of signals between two instruments that are as similar as they can be, but very, very far away. So that's why you all invested in this system. They are long because I told you that the amplitude of the gravitational wave is a fractional change in distance. And in general, we are limited by the amount of change in distance we can measure. So the longer we make it, the more sensitive we are. And making it 4 kilometers is about as long as people thought could be afforded, because these are vacuum tubes. Now, if these are 4 kilometers in length, and I told you that the fractional change is 10 to the minus 21, you multiply 10 to the minus 21 times 4, 10 to 4 kilometers, you get changes in distance that are less than 10 to the minus 19 meters, 4 10 to the minus 18 meters. Now, that may not mean anything until you try to remember some other distances, some other sizes to compare it to. For example, the atom. How big is an atom? Does anybody remember? Yes? No? A bit smaller than that. It's 10 to the minus 10. What about a proton? A proton is 10 to the minus 15 meters. So we are measuring parts in 1,000 of a proton diameter as the difference between these 4 kilometers and these 4 kilometers. Some people thought it was crazy, but not the people who worked on this. So how do you do that? Well, with a lot of technology. This is the part I used to dedicate a whole talk to before we discovered gravitational waves. And now I only have one slide. But, of course, if you want to ask me questions, I can talk for hours. So this is a simple Michelson interferometer. We have a beam splitter, 2 mirrors, and a photodetector. That laser has to travel in vacuum. So these are vacuum tubes. Ultra-high vacuum, 10 to the minus 9 torr, in a 1.2 meter diameter vacuum tube protected by a concrete enclosure. That concrete enclosure has protected us from fires in Washington, hurricanes in Louisiana, alligators in Louisiana, police cars crashing into that in Hanford. So they have served us very well. These mirrors are not mirrors that are bolted to an optical table, because an optical table here would move with respect to a beam splitter here a lot more than 10 to the minus 18 meters. So what we need to do is hang them in pendulums. And if you don't believe a pendulum does that, ask me again, I can demonstrate that for you. A pendulum can reduce the noise at frequencies above the pendulum frequency. And we do that hanging these in a quadruple pendulum from an active seismic isolation system where we have, notice the size of these, we have these layers, 3 layers with sensors and actuators in between them to measure the noise and cancel it. So we have the quadruple pendulum hanging from this active seismic isolation system that's sitting on top of some hydraulic system to work against earth tides and other motion, all of that in vacuum chambers. The mirrors themselves are state-of-the-art mirrors so that they have very, very little energy loss because that reduces the motion that affects us. And you would say, well, if that's a beam splitter chamber, then these two are very close. These are not 4 kilometers away, right? That's because we don't have a simple Michelson. We actually put mirrors in here near the beam splitter to make the light go back and forth a few hundred times. That's like making the interferometer longer. So it's not just 4 kilometers. We increase the sensitivity. And I will tell you that we are sensitive to quantum noise, so we do have others. So we have some quantum optical techniques, and we have lots of photons circulating in here by putting another power recycling mirror in here. So the technology we use in here, it's worth of 2 or 3 talks. But we don't have time because we have discoveries to tell you about. All of that is to get at the output on a photodetector that has noise in there. And then we have to look for gravitational waves in that noise. And of course, we have 2 data streams from the 2 detectors or from other detectors around the world. Now, the way we characterize the sensitivity of our detector is with what we call a noise curve. So this is the predicted amplitude, the projected amplitude of the noise as a function of frequency. What we want is to make these very small. We had an initial generation of detectors when they were first built in the 90s, and we took data in the 2000s, between 2000 and 2010, and the noise was up here. And then we took a break, and the National Science Foundation gave us money to install these advanced LIGO detectors. We had simple pendulums. Now we have quadruple pendulums and lots of other things like that. And then this is the noise that we project. So here the noise is bad because it's high. Here the noise is bad, not as bad as here because it's high. Here is where the noise is best. And why do we have this noise and not better? Well, at low frequencies, we are mostly limited by the seismic noise. The seismic noise moving the top of this active seismic isolation platform. So even though we do all of this, and we actually have a reduction factor of 10 orders of magnitude here, even though we do reduce the noise, it still dominates at these low frequencies. We call this a seismic wall because it's very steep. At intermediate frequencies, we are fundamentally limited by the atomic vibrations of the mirrors, because the mirrors are made of atoms, and atoms at any finite temperature, they vibrate. And that means that they are moving, and with the lasers, we are sensing that distance, we are sensing that. So we need two things. We need to make the laser beam on the mirror very big, so we average the position of many, many of these atoms, but also we need to make that, that vibration small. And we don't make it small by reducing the temperature. That's expensive and not that easy to do, but instead by reducing the sources of energy loss. And that's because that was a topic of my PhD thesis. There is a theorem that says that if you don't have any energy loss, which of course there's nothing like that, but if there is no energy loss, then all this vibration will be concentrated. It will exist, but it will concentrated at one frequency, the natural frequency of the system. If you think about the pendulum, it would be concentrated at that pendulum frequency. If you think about the mirror, it would be concentrated at the natural frequencies that the mirror vibrates, that the cylinder vibrates when you tick it. But if there is energy loss, then instead of being concentrated at that one frequency, it will spread. So, for example, this peak in here is the peak due to the frequencies of the wires that the mirror is hanging from. But that Brownian motion will spill at other frequencies. The one that dominates, it's the one due to the substrate, not to the substrate, but of the coating on top of the mirror. So we are sensitive to seismic motion, to atomic motion, and here at high frequencies, we are sensitive to quantum noise. Because in the end, we are measuring photons. We are counting photons. And photons are quantum, the quantum particle of light, and we are sensitive. We have a counting error. And we can do the math for that quantum noise, and we know we can decrease it if we use many photons. Because if you use many photons, then the relative error in counting the photons gets smaller and smaller. But of course, everything gets hotter and things get more complicated. So we do that. We use power, and as much power as we can afford without breaking things. But we also use quantum optical techniques to reduce, to squeeze the noise, to squeeze the quantum noise at the expense of increasing it in some other direction. Again, I can talk for hours on this. This is just to give you an idea of the complexity of this engineering marvel. And that doesn't happen just in the US with observatories. There is also a very similar observatory in Italy that is managed. It's called Virgo. It's 3 kilometers long. It's in Tuscany, near Pisa, in a beautiful region. There is a shorter detector, called Geo 600 in Germany. The LIGO detectors and the geodetectors are the ones that are operated and managed by the LIGO Scientific Collaboration, which is an international collaboration of now almost 1,800 scientists in 20 different countries all over the world. The Virgo collaboration is mostly a European collaboration, but also from other continents. And we work with the Kagra collaboration, which is a Japanese collaboration, and they operate also a 3-kilometer detector inside the Kamioka mine. So this is a worldwide network. I have to say that the US detectors are the best. But we all work together, and I will show you why is it that we do better science together rather than competing. 10 years ago, and a month now, in September 14, 2015, too early for me, it was 5 a.m. Central Time in Louisiana, there was this signal on the detectors. And I really get emotional, even 10 years later. What I'm showing you here is, as a function of time, the amount of light on the photocell. So the blue trace is the light. It's a signal in the photocell at the Louisiana detector. And you see that there is noise, and the orange is the noise, is the signal or the light on the photocell in Hanford, and you see that they don't look anything like each other. But then you see that the blue gets this oscillation that grows in amplitude and frequency. You can see that this time is shorter than this time, and this time is shorter than this time. So it grows in amplitude and frequency, and then disappears in the noise again. But then at this almost exactly the same time, 7 milliseconds later, there was the same thing in Hanford. You can see the thing in Hanford. There is some noise in there, but you can see it. It's there. We weren't taking data yet. Actually, we were looking at the data, but this was September 14. We were about to start the first observing run with advanced LIGO detectors on September 18. That was a Friday. This was Monday. And we were testing things. We were doing lots of different tests, and one of those tests was tests that were looking at analyzing the signal and giving alerts. And the alerts were emails at the time. Now they are phone calls, but or phone messages. Now, at the time, they were emails. So there was a computer producing an email saying, there's something here. Well, it was a plot, and it was a nice image. And the scientists looking at this in Europe and then early in Florida, they said, that looks like a gravitational wave, but it's so nice, it's so big, it can't be real. They called the detectors, they called the observators to see if this was a test, because we do tests like this. We push the mirror to simulate signals like this. And they said, no, there's nobody here, there's nobody doing anything. Well, then there were phone calls. I woke up to a lot of emails and a lot of phone calls. I was a spokesperson of the LIGO collaboration, like Keith said at the time. And they said, did you allow this to happen? Because we were prepared to do what we call blind injections to test our techniques. We had done that before. We had a small team of people that would push the mirrors in certain ways and not tell anybody. Of course, everybody would be aware of the experiment, but we had not started taking data, so we were not doing that yet. But everybody thought it was a test. I knew it wasn't. It took me hours, a day. The next day, I bought a big cake, but we had to prove it. It took several months to prove that this was real. We needed to do the statistics, and we didn't have any data yet. So it took a month to gather data, to look at the statistics. Then it took like 2 months to do the parameter estimation. This looks like black holes, but how big are those black holes? Where are those? Can we localize them in the sky? We had to know all of that. And then we wanted to have some external opinion too. So we wrote a paper, we sent it to physical review letters, to get referee reports. We had told them that we were going to send the paper, so they had referees ready at the set. We still don't know who they are. And they sent us reports, positive reports, but some suggestions. So it was only on February 11, 2016, when we could say, we did it. And if you allow me, I'm going to let you hear that, because it was very moving. That is Dave, it's the executive director of the LIGO laboratory.
Ladies and gentlemen, we have detected gravitational waves. We did it.
There were wave-wise Franz Cordova was presiding the press conference. She was the director of the National Science Foundation that had funded this project. This was 2015. They had begun funding it in the late 80s. 25 years later, they were seeing the fruits of this. And I was there as the leader of the LIGO scientific collaboration. It was an amazing day, but it was also a beautiful coincidence. We didn't do this on purpose at all, but that February 11 in 2016 was the first time. It's now celebrated every February 11. Does anybody know what is celebrated on February 11? No? Well, I hope that from now on you know. It's an international day. Sorry, I didn't mean to start the video game. It's the International Day of Women and Girls in Science. I actually met later on one of the women in Europe that had actually sponsored a lot of this and had mounted a Twitter campaign that day to celebrate the International Day of Women in Science. And she told me, we were so happy because we were first in Twitter trends until you made the announcement. Because it was the same day. But we were happy, she said later. Of course, who was we? Well, these were some of the people who were there, and you can see Keith in there. He was there. We were actually celebrating this. This was an amazing day. But there's a lot of us. That paper that was published on February 11, 2016 was signed by more than 1,000 authors. I think it was 1,004. And from the LIGO and Virgo collaboration, because even though Virgo was not taking data yet, we were working together. We had been working together since 2007 to analyze the data together. Like I said, this was a big cooperative effort. And that was a cover of PRL that day. The PRL servers fell that day. This is what the signal looks like. This is what it looks like in the time domain, but we like these drawings. These are time frequency diagrams. So this is time, like for the time trace, but this axis is frequency. So when the frequency is higher, then the signal is higher, and the color, the brightness, represents the amplitude. So you can see that it's brightest here at the top. It's brighter in Hanford than Livingston because the noise in Hanford was a bit smaller than in Livingston. So we call this a time frequency diagram, and there are very, very few signals. In fact, this was the only one for a very long time that we could see in the time domain. We could see the signals in the time frequency domain like this, but like this was the cleanest one for a long time. And I like to say that these are black holes that you cannot see because they don't emit light, but you can hear with gravitational waves. So I like to call this a music of the universe, and of course what we can do, even though these are not sound waves, is to put them on a speaker. I mean, it's a digital signal, it's an MP3, so we do that. And let me see if I can do this. Did you hear it? Let me play it again, what you actually hear is a rumble, which is the noise. And then there is the bump, which is not very nice. And it's not very nice because the frequency, it's a low frequency, it's in the 200 hertz. And that's not a nice sound. So what we did is we added 400 hertz. We said, if the astronomers paint the ultraviolet in blue and the infrared in red, why not increase the frequency? So that's what we did. And that's what it sounds. So that's the original one. This is the one we played at the press conference. But we have danced to this. I have danced to this. I have a dress with this waveform too. 2017, as you might remember, there was also a Nobel Prize for this, and we were very, very happy about it because it was Ray Weiss and Kip Thorne from MIT and Caltech, the two pioneers that in the 70s had begun doing this. 70s, I mean, this was 45 years later. And Barry Barish, who had been an executive director of the LIGO laboratory in some difficult times, and also somebody who pushed to create, in 1997, the LIGO scientific collaboration. But what we were most proud of was that as affiliations in the press release from the Nobel Foundation, they didn't use Caltech and MIT. They used LIGO and Virgo collaboration. So we feel we're all Nobel Prize winners. Now, and this goes back to these other matters I wanted to tell you. I know that most of you like physics, but when you think about the physicist, you probably think about Einstein, and you probably think about a picture of Einstein like this, or you think about Nobel winners, Nobel Prize winners, like the ones we heard about this week, or last year, or the previous year. It all look like this. But when they did their Nobel Prize work, they didn't look like that. They were young. So people who do the best physics are the young people. And you can tell, if you look at the Nobel Prize winners, they earned the Nobel Prize when they are gray-haired and old, but they were young when they did the work. So when you think about physicists, you should first think about young people. Those are the ones that are the geniuses, if you want to think, although I don't think you have to be a genius to do physics. But it's also lots of people. And lots of people that are not all men. They are people of all kinds, of all nationalities, of all genders, of all sizes. And that's because you need everybody's ideas to put it together. I told you about these instruments that we have built, these beautiful, sensitive instruments. We needed all kinds of specialties. We needed engineers, optical engineers, electrical engineers, technicians, builders. You need a lot of different expertises and a lot of different kinds of people to build these things. Of course, when you begin to put all people together, you lose sight. So I like this picture. This picture was the picture of people in my group, the young people in my group who were in Louisiana, not in Washington, on the day of the announcement. And they are all doing great things now, working in NASA, some working in LIGO. I think she's the only one still working in LIGO. Well, he's working on LIGO and some computing, but everybody else is doing other things. But they were the ones that did the work. They and all their generation were the ones that were doing the work at that time. Okay, back to science. 2016, 2015, 2016, we were taking that first observing run that we started in September. We ended in January. And these numbers give you an idea of how far away we can look at neutron star mergers, not black holes, but neutron star mergers. But we didn't stop there. We didn't have the sensitivity, this number 80. I didn't show you, but in that projected noise curve that we had for advanced LIGO, this number had to be, we wanted it to be 170. We were at less than half of what we wanted. And that's because we had too much noise. We had to reduce the noise. So we stopped, and then we got better, 200 to 100, and then we began taking data with Virgo in the second observing run, and then we stopped again, and then we started again in 2019 to take data in the third observing run, and you can see these numbers getting better slowly. This takes a lot of work and a lot of time. So I want to tell you about what we discovered in here. Remember, the first detection was right at the beginning there. What did we know before us about neutron stars and black holes? Well, you can see black holes, with telescopes, because some black holes are close to other stars, and there's matter falling from the other star, and that matter is falling very fast, and it's producing X-rays. So we call those, astronomers call these X-ray black holes. These are the X-rays produced by the matter falling in there. So these are the masses. This y-axis in here is the x-axis doesn't mean anything. It's a way to distribute the signal. So these are the masses, or what we call electromagnetic or X-ray black holes. And you can see that they are between 5 and 20 solar masses. Neutron stars, we can tell because they emit radio beams to Earth that arrive to us in pulses, so we call these pulsars. There's a beautiful documentary about the discovery of these by Jocelyn Bell, almost famous. I recommend that in YouTube. So this is what we knew about masses of neutron stars between 1 and 3 solar masses. I don't know what was that. These were the 3 signals. We actually, in that first observing run in 2015, 16, we saw this one. Notice the size of these black holes. These were 29 and 36 solar masses, forming a final black hole of 62 solar masses. And there were 2 other detections in October and December. So we only had 3. But these, especially this one, but also this one, they were at the higher end of these masses. This is what actually gave us pause. Does nature have really these black holes? Is this a real signal? It's too good to be true. That's what we kept saying. It's too good to be true. But it was true, and it was real. These were big black holes. So this was the first observing run, discoveries in 2015, 2016. In the second observing run, we added quite a few more. But we also added this one. These are 2 neutron stars merging into a single black hole. And that was an amazing signal. If you look at the time frequency diagrams, these all look about the same. Look at the brightness of this one. This was the brightest. It had the record brightness for a long time, as I mentioned. But this one is completely different. And this one is much longer, which means that the masses were a lot smaller. We can only tell the masses. Well, we can tell a bit more. We can tell a little more than the masses. And these were the masses of the black hole. This was the smallest black hole, but these were these 2, much smaller. So these 2 were consistent with neutron stars, not black holes. But not only that, we were also taking data with Virgo. And that turns out to be very important because with 2 detectors, when you say, well, where did that signal come from in the sky? You can say, well, from about there. Astronomers are not very impressed with that. They are, with 2 detectors, you had, with the first detection, we had that 7 millisecond difference in time. That gives you a ring in the sky. And if you look at the face, then that looks at half the ring. So that's what you see in here for localization of many different gravitational waves. But if you have 3 detectors, now you can triangulate. So look at these signals. Those are much, much better localized. So we were so excited when we saw this one, August 14, the first detection with 3 detectors, and we could localize. So we had a triple, we called it the triple detection. It was 3 detectors. It was amazing, and we could see the signal in the time frequency diagram in the 3 detectors. And we were so happy and planning a publication on that when 3 days later, we had this one. And this is a neutron-star merger. And that was amazing. Not just because it was different, it was a different signal, but because it was also seen by gamma ray detectors. So let me play again the music of the universe. This is now the signal without the noise. It's just the wave, the gravitational wave. That's a coalescence time. And the Fermi and the integral detector, less than 2 seconds later, saw a small burst. It was a gamma ray. And they had been measuring these short gamma ray bursts for decades almost, more than decades now. And they thought that they were coming from mergers of neutron stars. But they had never proven that because they couldn't see in other ways the merger of neutron stars. But here we had it. We had seen the merger of 2 masses consistent with neutron stars, and we had seen, and they had seen, a merger, a burst of gamma rays. At the time, we had agreements with lots and lots of astronomy groups. We sent the alerts, and they all received it, and they all began looking at the sky at this region that we could localize because we had detectors working. If not, it would have been all of that and all of this from all of these. So our localization seemed to be good, but there were 40 different galaxies in there. They began looking at one by one until they found this galaxy that had a bright spot that had not been there before. And these are all the different wavelengths. We saw the gravitational wave ending here. There was a gamma ray. And then there were signals seen in the optical and in the infrared and in the ultraviolet, and the signal was blue and then became red. And 10 days later, there were radio and X-ray signals, all from the same tiny spot in the sky. So this is a kilonova, I like to say, a kilonova rainbow. Unfortunately, it's been the only one so far, but I don't know, maybe tonight, maybe tomorrow, there's another one. So in 03, in 01 and 02, we saw this amazing, we had a catalog now that had 10 black hole mergers and 1 neutron star merger. In 03, we had all of these. This is when we stopped for COVID and for a long break to install more upgrades in the detectors. And you can see the number of black holes. There is also a second neutron star merger here, but this was farther away, so it didn't have a counterpart. And there are several neutron star black hole mergers. So this is a neutron star and a black hole that produces a slightly larger black hole. We have lots of information. I like to say that we've become a black hole observatory, although I would like to see more neutron stars than this. So this is where we were when COVID came, but we have a new catalog because we kept taking data. We started taking data again in 2023, and up to January of 2024, we saw all of these. This catalog was published only a couple of months ago. And we have now published 218 signals. Again, most of them black holes. Unfortunately, these are still the only 2 neutron star mergers. We have a couple more neutron star mergers. We have some in which the smallest object is in what we used to call the mass gap, because there were very few things in here. But now there's quite a few, some resulting from the mergers of the neutron stars that we have seen, and some as the primary one. Some other signals are so large, this is the largest of all, that astronomers tell us that they are probably not produced by supernova explosions. They are probably produced by another merger of black holes. So I like to say that we are seeing families here. This is a grandchild, and there were 2 parents, and there are grandparents in there that we don't see. That's how we think these black holes are formed. Some more details about some of these events. This was in 2023. This is the date of the event, 2023, May 29. This was one of those objects that was smack in the mass gap. So that is what made this one very interesting. This one It's our new favorite. And this is the latest one that we have published about. It's huge, 137 and 103 solar masses. That's huge, and that's not only good for understanding how black holes form, because these are, again, probably not from supernova explosions, probably mergers of other black holes. From the rest of the black holes, we can measure a mass distribution that has some features in there that astronomers are trying to understand. These are way out here. But with this, we can also test general relativity. And for this one, we actually got very tempted and published a test of Einstein, Hawking's theorem. Hawking published a theorem in the 70s saying that if you have two black holes, each one has the area of the event horizon, and when they merge, the area here, it's larger than the sum of these two areas. And it was with the first detection that had a big amplitude, we could tell this was true, but not with high precision. With this one, we can tell it much better. So this was the story for this one. But what I like best is this figure. We also published in PRL. This was, again, the cover of PRL. But compare this signal with this one 10 years later, almost exactly 10 years. What you see is that reduce the noise a lot more. The signal is almost the same strength, but we had made the noise a lot smaller, and that's what makes us better. So the number of detections, the total was on September 29, 377, but we are detecting 1 or 2, sometimes 3 a week, so we have a few more. I think we have 3 more than those. We are getting close to 400 now. You can get alerts. I actually get alerts on my phone with an app about these detections, so these are all public. The alerts are public. When we publish the data is public. You can go to our website and see it. This is the present. We are taking data now in 04, the fourth observing. We had 3 pieces, O for A, which is what we have published, O for B, that we are analyzing, O for C, we're taking data now. Then we're going to take a long break, and then we don't know. I hope you all help us tell our representatives that science is good, and funding science is good, and funding LIGO is good. We think it is, of course, but we need to give them reasons to do that. And the reason is all those young people that we train and do lots of useful things. But we also think longer term than that. We have concepts for sensitivities that are not just a little better. We have that too. We have upgrades that we want to install that will make our sensitivity a little bit better, maybe a factor of 2 better. But we can make it 10 times better if we make our detectors 10 times longer. So there's a project called Cosmic Explorer that is looking for sites to build a 40-kilometer detector. And there's a conceptual design, there's a price estimate. We are talking to the National Science Foundation about it. It's a long-term plan, but this is like the 70s and the 80s were for LIGO with Ray and Kip. And in Europe, there's a concept called the Einstein telescope, which is a triangular 10 kilometers on the side detector, underground, cryogenic. Both of these are being pushed in the respective science agencies. But this is only one corner of the frequency spectrum. When you talk about optical telescopes, you know that, well, not optical, when you talk about telescopes, you know that you have radio telescopes, X-ray telescopes, and everything in between. With gravitational waves, it's the same. We are at the high frequency corner of the gravitational wave spectrum. But the massive black holes at the center of the galaxies, they produce gravitational waves with lower frequency. The supermassive black holes, they produce gravitational waves of even lower frequency. The early universe produced gravitational waves of all frequencies, including those of the size of the universe. So we are not detecting those. We are detecting the small black holes, hopefully supernovas, rotating stars, and that kind of things. But for the massive black holes, there's a space interferometer called LISA. For the supermassive black holes, there's a technique called pulsar timing. And for the cosmological background, there's another technique which is not interferometry, which is looking at the polarization of the cosmic microwave background. And all of this is happening. LISA got the go-ahead for beads, for industrial beads to build it last year in 2024. So it's going ahead. It has a launch date of 2035. And Pulsar Timing published a couple of years ago something that looks like a signal. And it's not a short signal like the one we have, but it's this humming noise that might be produced by all those massive, supermassive black holes far away mixing up with each other in a noise. And I like, this is some people of the Nanograv collaboration, the North American collaboration. I think there are some people here, members of that collaboration. But this signal was seen by the Australian collaboration, the European, collaborating with the Indian one, the China one. All of these people saw the same thing. And you know that I like music, so this is how they sing it. It's a hum. It's not a chirp, but it's still music. It's still the music of the universe. So that's gravitational wave astronomy in a nutshell. A long nutshell, but I hope you enjoyed it. Thank you.
Thank you for the wonderful talk. The lecture is open for the questions. Please use a microphone for our live audience on the stream. And if you cannot get to the mics, we have student helpers to bring the mics to you. So again, please go to find the mic and ask your questions.
And I love questions, so please ask them or I'll be very disappointed.
So earlier you had mentioned how you recycle the beam many different times through the 4-kilometer wings. How does building a 40-kilometer wing make you more sensitive than just recycling it more times in the 4-kilometer?
That's a very good question. When we make the signal go back and forth, we are adding up the signal in all those trips. But we are also adding up the noise of the motion of the mirror. If you make it 10 times longer, then you don't need to go back and forth that many times, so you are going to be less sensitive to the motion of the mirrors. Another way of saying is that you will divide the same motion of the mirrors not by 4 kilometers, but by 40 kilometers. So it's 10 times smaller.
Please.
Hi, that was a great talk, by the way. Though I have a lot of questions about the actual sensor technology, you mentioned in your kilonova section that you guys saw a light rainbow about 3 days after the gravitational waves were detected. Why was that 3 days after?
10 days.
10 days.
Yes. Those were radio and X-ray signals, and they were, astronomers tell me, so yes, that was this and this. And astronomers tell me, because I'm the physicist, not the astronomer, that this was these optical signals, or near optical, near visible signals, were the matter, gold and platinum and heavy atoms. Actually, that's another thing that is interesting about this. This helps to explain the origin of heavy atoms. Those atoms, that matter was expanding. And it got to the dust that is around it, to the matter that is farther away. So this system had eaten everything around them, but then there was dust and other matter farther away. So this was a shock wave of the atoms from the merger getting to that surface.
talked about one of the cool things being that you now have detections from 3 different interferometers at once. I wanted to ask about going the other direction. Now that you know what you're looking at and you have a high degree of confidence in your instrument, do you have a lot of single interferometer detections as well? Are those published as a part of the catalog? Are those useful, or?
Yes, we have published several individually and then as part of the catalog. So there's a huge table in the publication where it tells you whether it was HL or HLV or L or H, which detectors saw the signal. We can detect signals with a single detector only because we know about the noise in the detector. And we know about the noise in the detector because we know the signals that are not seen in both detectors. So we learn about the noise because we have 2 detectors. Everything that's not seen in both, that's a noise, and then we learn about the noise. But if we operate one detector now in between because the others are, we can assume that the noise today was the same as yesterday. But if we take everything down and operate only one detector, then we're only going to see the bigger signals. That's why we are thinking about Cosmic Explorer as a single detector that will detect many signals, but it will not detect the smaller signals unless we have another one, and that would be the Einstein telescope.
Please.
Saying that talk was wonderful. But my question is, in 2015, the very first discovery of the gravitational waves, you said the LIGO sensor in Louisiana received it, but then the sensor in Washington received it 0.7 seconds later.
7 milliseconds.
7 milliseconds
Yes.
later, sorry. What explains that delay in the signal receiving?
Another good question. Yeah, that's the speed of light. So if the signal, if the gravitational wave was traveling straight from one detector to the other, it would take 10 milliseconds. But if it comes from any other direction, then it will get to this one first and to the other later, but with less than a 10 millisecond difference. And this was true here. It was 7.
So much. And if it's okay, can I ask one more question?
Please.
Okay, so the G600 sensor and the other sensors that are less than 4 kilometers long, what is the benefit of having those if they can't receive a signal with the same strength as the one that's 4 kilometers long?
Well, you build them as long as you can afford. So there's no fundamental reason for 3 or 4 or 5 kilometers. It's all a trade-off between cost and science. But for Virgo, being 3/4 is one disadvantage. On the other hand, they could compensate that with technologies. For example, at low frequencies, they have the potential. They haven't realized that. But at low frequencies, I told you that we have a quadruple pendulum. They have a septuple pendulum hanging from an inverted pendulum. So there are ways that are expensive and complicated of making things a bit different and better, even if they are not as longer. But the G600 detector is significantly less sensitive than Virgo or LIGO, and that is being used mostly in astrowatch mode. Whenever we go down, they are up. In case of a supernova or something very strong, they are up, and maybe they'll see it, or at least we won't be so ashamed. But also, we develop technologies, all this quantum squeezing, quantum optical squeezing of the vacuum that we do to be more sensitive. That was tested first in GEO. GEO had double and triple suspensions before we had quadruple suspensions at LIGO. So we tested lots of technologies there first before installing them in LIGO.
Thank you so much.
Please.
You're talking about having these low frequency signals that can help detect this supermassive black holes. If those are not mergers, how are they detected? Because isn't it that if they're spherical, they don't give off gravitational waves, or are they interacting with something?
Well, the sources are not spherical because the sources are binary systems of massive or supermassive black holes. So they are not single black holes. I'm sorry, I didn't say that. The sources, when I say black holes for these are all binary black hole sources, which we know exist because massive and supermassive black holes are at the center of galaxies, and there have been many galaxies seen with two black holes or two galaxies colliding. Each galaxy has one black hole. So those are known to exist. The binary black holes that we saw, nobody had seen one before because I told you that they saw them with X-rays. But X-rays means that there's a regular star. If you have two black holes, you don't see them.
Please.
Thank you so much. I knew these LIGO sensors and other sensors were incredibly complex, but I had no idea.
That's why they took so long.
My question is, you mentioned a little bit about Stephen Hawking's and how you proved one of his theorems or supported it. When one of these systems chirps, what's the relationships between the size of the objects before and after the chirp, and how much of the energy is lost in the wave itself?
All are very good questions, actually. We calculated that. We don't do it for every black hole, but we did it for the first signal. In the first signal, we had two black holes that we estimated 29 and 36 solar masses. Well, the final mass of the black hole, we estimated it at 62 solar masses. Now, 29 plus 36, it's not 62, right? There are 3 solar masses missing in that sum. That was the energy converted into gravitational waves in the merger. E equal mc squared. So from 3 solar masses, if you convert that into energy, for example, invisible light, that's more than all the stars you see in the sky combined for that fraction of a time. So there's an incredible amount of energy in the merger itself.
Thank you for the talk. I was going to ask the same question this last gentleman just asked, what happens with the energy in the solar masses? But talk about that in the context of how distance, if you will, from the merger, if you will. What would it feel like if you were a light year away versus 1,000 light years away or 1 billion light years away? What would the difference feel like in that energy from the gravitational waves?
Well, we also calculated that, and I don't remember the exact distance, but you wouldn't feel anything unless you're really, 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 really close. And that's because the energy of the gravitational wave is huge, but the effect of the gravitational wave is this delta L over L, and it decays with distance, like 1 over distance, not distance squared, because we're measuring field, not amplitude. So the farther away you are, the smaller it is. But it was 10 to the minus 21 here. So even if you were, and this was 400 megaparsecs, which is 1 billion light years away, if you were 1 light year away, then the signal would be 1 billion times larger. That's 10 to the 9 times 10 to the minus 21. That's 10 to the minus 11. You wouldn't feel it.
Not be perceptible, you're saying?
Not by humans, no. Of course, by interferometers like this, by other planets, by humans or live beings in other planets, maybe, but not on our bodies.
Trying to make an analogy to an earthquake, the distance away from when it occurs.
Exactly, right. It gets weaker with distance, but it's so weak that you wouldn't feel it.
Thank you.
Thank you, Larry. Please.
Yeah, thank you. So on September 13th, 2015, there was a solar eclipse, and September 27th, there was a lunar eclipse. So is there any research done that shows those two occurrences affected your discovery?
I don't remember that eclipse. I remember, I remember September 13 very well because I was interviewed that day. There was a film crew at the LIGO Livingston Observatory that was going to begin filming a many years history of the discovery of gravitational waves. And they were there September 13, 14, and 15. So September 13, there was an interview. That's why I remember that day. I don't remember an eclipse, but I believe you. No, they wouldn't have any effect. We are not affected by the atmosphere. We are affected a little bit by wind, because the wind tilts the buildings, and that produces noise at low frequencies that we have to compensate, and sometimes we don't have enough force to compensate. But other than weather, it doesn't affect us.
Thank you. Thank you.
By the way, there is a movie, a documentary movie, the documentary produced by this director. His name is Les Goodman. It's called LIGO, the movie, not a very original title. He actually produced several documentaries, but this is a 90-minute feature-length documentary that tells the story in first person of that discovery that you might be willing. It's on YouTube, so you can watch it if you want. It's a bit long for my taste, but you can see us doubting. Was this real? Was this real?
Please.
I guess I'll dip into the pot one more time. But I guess in the last 10 years, I mean, AI has moved pretty far forward. And with that have come a lot of brand new noise deconvolution algorithms. And I was wondering, how does that help you guys with helping reduce some of that noise at LIGO?
Well, we try to take as much advantage as we can. We have been using machine learning algorithms a lot in different ways. For example, in finding patterns in the transients, in the non-astrophysical transients, in the noise we have in the detectors. There's also machine learning techniques being used for accelerating the parameter estimation of the signals, which is what takes the longest, a lot longer than the analysis that finds the signals. We actually have that analysis running in real time now. So we have advantage. There are some new studies on maybe helping with the very complex that we have. Not so much for reducing the noise, but for making it more stable. But I believe that they need a lot of human training and human interaction with humans yet.
All right, we have time for very last question. Yeah.
I'm wondering if you could give us some idea of the orbital period toward the end, how fast they're spinning around each other.
Well, for that first detection, it was 0.6 the speed of light, 0.50 something the speed of light, half the speed of light.
Significant relativistic effects then.
Sorry?
Significant relativistic effects?
Oh, yes, yes. And actually, we use, especially the strongest signals, we use them all to test general relativity. So, and we haven't found anything that disagrees with general relativity yet, but maybe sometime it will fail, and maybe it will give us clues for a better theory. But so far, Einstein has been right.
Wonderful. Thank you for the wonderful talk. Let's thank the speaker again. Thank you, Gabby.